part. So yesterday we were, just a second, big slide. So yesterday we started Bayesian networks, which are which is basically a directed acyclic graph where the dependencies denotes the relationships like parents, child, or descendants, and the ancestor. And we have seen that on a Bayesian network, we can derive the total joint probability based on the local conditional probability of each node, because we do something called a Markov assumption that the value of any node or the probability of the random variable assigned to a node is only dependent on its parents and is independent of its non-descendants. So we have seen for the any xi, the probability is xi conditional to the probability of its parents, and then as all these local conditional probabilities are independent of each other, for the full joint probability we just multiply them. So in this also has an advantage that the number of computations required are less, and in this way we can calculate over a very large directed acyclic graph. And also another point to note, all these variables for the time beings we have considered them to be the Boolean variables. That means they have only two states, true or false. That condition also helps us reducing the columns in the conditional probability table. So a conditional probability table depicts that depending on the different states of the Boolean parents of a node, what will be the true value of the node. That is the probability of the node to be true. Okay. So now yesterday we stopped at this, that till the previous slides we have seen that how we can calculate and the probability of a particular node or a joint probability over a set of nodes in a Bayesian network. But now we are trying to also construct a Bayesian network, and how we can do that by rule or by methodically. Say if I have to write a code. So for that, for constructing any Bayesian network, so it is basically a directed acyclic graph. So for graph, the very first thing that we need is uh, the the set of nodes, that is the condition, that is the random variables, that is actually each variable in our uh, problem statement. So we choose an ordering of the variable and assign them x1, the number x1 to xn. So these are just the random variable numbers. These values does not signify any other thing. And then we iterate I from the 1 to n, and we add xi to the network. So say first we add x1, and then the what do we need? We need a node and its parents, right? Because the probability of a node depends on the probability of the parents. So we say, for example, we add x3. So we now need to select the parents from x1 to x2, x1 and x2, such that P of x3 given P of the parent of x3 will be equal to P of x3 given x1 comma x2. That means we need to choose the parents such that if we calculate the conditional probability of xi given its parents, it will be equivalent to the conditional probability of xi given all the previous states or all the other nodes. Okay. So this kind of choice guarantees two things. First one is that the chain rule holds. That is, if I want to calculate the joint probability of P of x1 to xn, that is joint probability of all the random variables, I can simply do that by multiplying P of x1, say this is xi given x1 up to xi minus 1. That is, it will be like p of x1 into p of x2 given x1 into p of x3 given x1 into x2, p of x4 given x1, x3, x1, x2, x3 and so on. So now, but as definition, we have also chosen this condition. So basically we can reduce this to this. That is the local conditional probability of xi given its parents, which is basically this, which is actually our rule of the Bayesian network. Now, how do we construct it in practice? So let us go
Ma'am,
back.
I have a question.
Yes.
Ma'am, for any ordering of variables, um, will this is guarantee the correct probability? Because let us say that if the parents come afterwards, the child notes, then in the conditional probability it will not become correct.
No, see, the thing is that we were precisely going with that in the next example. The thing is that the conditional probabilities are between two variables, right? It can be x given y and y given x. So what you can say that depending on the ordering, we may not come up with the same network, but the probability values, like, they won't be correct or incorrect, because we are assuming that we are having the conditional probability for those combinations already present. So let me demonstrate this by an example. Okay, your question is very valid, and that's why I stopped yesterday also at this point. So if you recall the use case that we dealt yesterday, so it was like, I am at work, neighbor John calls to say my alarm is ringing, but neighbor Mary doesn't call. Something Sometimes it's set off by minor earthquake. Is there a burglar? So to do that, we have identified five variables, that is burglary, earthquake, the alarm being set off, and John calls and Mary calls. And we created a network based on this causal knowledge that a burglar can set the alarm off, an earthquake can set the alarm off, an alarm can cause Mary to call, the alarm can cause John to call. So that means the alarm is dependent on burglar and earthquake, and the alarm in turn influences John calls and Mary calls. And we had these conditional probability tables. Now these tables are given. So we are not calculating this at the point. Okay. So say for example, someone did a survey and find out that the probability of earthquake in the very region is only 2 out of 1,000 times. Okay. So these tables are given. So we are not going into that, but what we did is that given this table, how can we find such a probability like this? Say John calls, Mary calls, and the alarm goes off, but there is no burglar and there is no earthquake. Okay. So now we have the same situation, but let's say we choose the ordering, the ordering as Mary, John, alarm, burglar, earthquake. Then how will my network look like? So first I add Mary calls to the network. So Mary calls is just the first node. It does not have any parents to consider from. So I move on to the next node. So now I am on to X2, which is John calls. So I add John calls. Okay. So now I need to see that if there is any parent for John calls present. So for that, what I need to do, I check that whether the probability of John calling given Mary called is equals to probability of John calls. What does that mean? If these two are equal, that means the probability of John calls is independent of whether Mary calls or not. But as this is not equal, we establish a connection from Mary calls to John calls, because definitely somehow Mary's calls influences John. So now the thing is that where are we getting this information from? For the time being, we are assuming that it is given. Okay, for the example. Now Mary calls to John calls John. Now we move on to the third note. That is the alarm. Now for the alarm, there are two potential parents to consider, John and Mary. So what we need to check is that whether the probability of the alarm given John and Mary is equal to the probability of the alarm given John. That means the alarm is independent of Mary calls, and whether the probability of alarm given John and Mary is equal to the probability of alarm. That is, alarm is independent of both John and Mary. It is no. So we add both Mary calls and John calls at the as the parents of the alarm. Okay.
Uh, uh, Ma'am,
Anyone is saying something?
ma'am, I have a question.
Yes.
Uh, uh, so you said that this if the second statement is equal,
Hmm.
shouldn't it be that the Mary cause is independent of uh, alarm goes off intersection John calls and not just alarm, right?
No, see, this means this the arrows means the alarm going off is dependent on Mary calls and John calls. Not Mary calls is dependent on the alarm going on. Don't think about the previous network now. We are dealing with the other set of conditions. So in the previous network, we dealt with M given A. Now we are calculating A given M. Okay.
Okay.
So
Ma'am,
now,
Ma'am,
yes.
can you please explain the second one? Probability of alarm ringing given J and M.
Okay. See, by the method of Bayesian network or like constructions of Bayesian net, say when we are adding at the alarm to this network, the alarm is the third variable, right? So it is x3. So when we are adding x3 to the network, I need to choose the parent of x3 from x1 and x2. So ideally, x3 should be dependent on both x1 and x2. That is my chain rule, right? To calculate the full join probabilities. Now I check on which of x1 and x2 is it dependent, or only one of them is it dependent. So I first check that whether the alarm given John and Mary, like two previously present nodes, whether this this is equals to P of the alarm given John. That means P of alarm given John will be conditionally independent of Mary. So that means only there will be only one line from John calls to the alarm, only one arrow. Okay. Second, I also check whether P of alarm given John calls and Mary calls J and M is equal to P of A. So this means that if it holds true, that means alarm is independent of both John calls and Mary calls. But both of these conditions are false. That means alarm is dependent on both the parents, Mary and John. Okay. So that's why we add these two arrows from Mary calls and John calls. Is it clear?
Yes, ma'am. Yes, ma'am.
Okay. Now,
ma'am, I have a question.
yes.
Uh, Ma'am, in the previous case, what we considered that probability of J given M equals to probability of J, we were checking that because for J the only possible parent was M. So when we are considering A, our only possible parents are M and J, right?
Yes.
So in that case, why are we not checking probability of A given J equals to probability of A and probability of A given M equals to probability of A? Like if we check only these two, then we can just independently trace the arrows.
No, we cannot check it like this way because first of all, by the chain rule, we need to calculate it over both x1 and x2. Okay. We cannot see to calculate independently, to calculate x3 given x2 and x3 given x1, we also need to establish that those are conditionally independent of each other, which actually we were doing at this step. This says that probability of A given J is conditionally independent of memory calls, which we found to be not true. Okay.
Okay, ma'am.
because
But
because no, see, this comma, this does not mean that we can take a given j comma p of the given m. This comma actually the joint probability of j and m, and as j and m are not conditionally independent of each other, we just cannot break it down. You understood? So this is from the basic rules of probability.
ma'am, I am actually confused. Like, what will be the arrows in the case? Let's say we are checking two conditions. So there are four possibilities: yes, 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 no, no, yes, no, no. So what will be the arrows in that case? I was confused about that.
Can you please repeat the question?
Uh, yes, ma'am. I am saying that we are checking in the second line. We are checking two conditions, right? And we are getting both of their answers to be no.
Yes.
So if it is in the other case that one is yes and another is no, so then what will be the arrows accordingly?
Okay. Okay. First of all, if this is yes, then we won't have this at the arrow. Only this arrow will suffice because the probability of given j is independent of probability of m. So that means only j is the direct parent of a, and if this condition was true, we wouldn't have the either of these two arrows. That means the alarm is an entirely independent variable of miracles and John calls. Okay.
Okay, ma'am.
Okay, just give me a moment. Huh? Just give me. Okay. Hi. Sorry for the interruption. Okay. So let us move on to our fourth note, which is B, that is for burglary. So we add burglary. Now we check that whether the probability of burglary given A, comma J, comma M is equal to probability of B given A. That means can only the alarm be the immediate parent of the burglary? And we found that it is yes. So we add only arrow from alarm to burglary. Okay. And we have also evaluated that whether burglary is independent of all the other nodes, and we have found it no. So similarly, when we add earthquake, we see that whether the probability of earthquake is equal to B comma A comma J comma whether P of E given B comma A comma J comma M is equal to P given A or is equals to P given A comma B. So that means whether earthquake has only one parent alarm or it is dependent on both alarm or burglary. We found this to be a no. And we found this to be a yes. Just a second.
Ma'am, where from we are getting the probabilities?
We are assuming that it is given.
Okay.
So this to be a no means the earthquake is not only dependent on alarm, and this to be an yes means earthquake is dependent on both alarm and burglary. So we add these two arrows.
Ma'am,
Yes.
do we
Yes.
need to check the second immediate parent also, ma'am? Like in the previous cases, we only checked of alarm. We didn't check for J also in the burglary case. But in the earthquake case, we have checked for alarm and burglary both.
Yes, so actually we check for all these combination. So when we at the burglary, we only check for alarm because J and M were both the parents of the alarm. So we started looking that whether only P given A will suffice. If it wouldn't suffice, then we would have gone to the other variables as well, which is happening in the earthquake case. When we see this is to be no, then we add B and check that whether now it is true. Okay. So we
Okay,
do
ma'am.
not beforehand how many to take. We go on by taking it up increasingly. So basically, what happens? This for loop contains another for loop to select the parent. So all clear till this point, everyone?
Ma'am, uh, the third
Yes.
statement that you said. So, uh, so if I expand that chain rule, and the left hand side should be equal to probability of B given A. For that to happen, uh, A intersection B should be independent of J intersection M, right?
Sorry, I didn't follow. Tell me.
Like I am just expanding the third statement, which is yes,
This one. This one.
yes. So,
Yes.
so for the left hand side to be equal to probability of B given A, uh, like the probability of B intersection A should be independent of J intersection M, right?
Okay.
So what does that mean? Can you explain that? And uh, and in the denominator also, A is independent of J intersection M. So what? How do I interpret this?
No, no. See, A is not. So it is not A independent J intersection M. So basically, see. when you expand this, say you want to calculate probability of B given A. Then when you go for the probability of A, this probability of A is again dependent on probability of A given J comma N. So that is the beauty of the chain rule. You do not need to calculate this whole at the same time. You can calculate it by multiplying up the local conditional probability. See, it will be helpful from this thing. From this example, if we need to calculate the probability of J intersection M intersection A, this was the previous net. Okay, this network. So what I am calculating, I am just calculating J intersection A because A is my immediate parent and sorry J given A, and I am also only calculating the probability of the M given A. So because it is only dependent on the parents, it is not like that we are omitting everything else, but we can expand it by multiplication like a chain. So each chain unfolding once at a time. So basically see, what you are saying that when you need to actually calculate the probability of B, for that you need to have the probability of A from Bayes rule even for calculating this. Now the probability of A will be in turn dependent on the probability on J and M. So that's how all the other probabilities will be looped in.
Okay, okay, ma'am. Got it.
Okay.
But if we wouldn't have assumed the Markov property, we would have had to expand this whole thing, right?
All, yes, all. So that was the need for assuming the Markov property. That it is only dependent on its parents. Now, when we go to the parent, we will check the parent of the parent. Okay. So, what the advantage is that in my conditional probability table, I only need to have these. I don't need to have all these values. And then by multiplication, we can found the full joint probability distribution.
Yes, ma'am.
Okay. Okay. So let us move forward. So now, as we are saying that two nodes are conditionally independent. So how do we, so independent means they have certain kind of distance or separation within the directed acyclic graph. So how does I represent or denote or ensure the conditional independence in a graph? By using a measure that is called D-separation. Okay. So two sets of nodes X and Y are conditionally independent given an evident set of nodes E if every undirected path from a node in X to a node in Y is D-separated by E. Okay. That means in my graphs, I have different combination of nodes X and I have two nodes, so two different nodes X and Y, and there can be a group of nodes, a subset of combination of nodes that we are called E, and we are saying X and Y are D-separated by E if every undirected path from a node in X to a node in Y is D-separated by E. That means like X and Y are sets of nodes. So basically I am taking, you can think like three groups in a graph. Now if the two groups at the two end are separated uh, uh, by E, so we are saying that it is separated by E and these two groups of nodes are conditionally independent of each other. So a set of nodes E separates two sets of node X and Y if every undirected path from a node in X to a node in Y is blocked by D. That means say my E sits in middle. So every path that will try to go from A to Y is blocked by E. So E holds, like you can say, like the E is the link between X and Y, and there is no other no other path from X to Y that exists. A path is blocked given E if there is a node Z on the path for which one of the following holds. So let us see graphically. That is, this is a set of node X and this is a set of node Y. So for every path from X to Y, and see, we are considering undirected paths. So the actual direction does not matter. Basic, and see, every path needs to go through this block of nodes, which is called the E. So basically, the idea is that if you recall the spanning tree, that is, if I take out E from my network, there will be no path left between X and Y, even no undirected path. So then E uh, he is said to de-separate X and Y. And if such a block of nodes exists, we say that X and Y are conditionally independent of each other. What does that mean? That X is not the direct parent of Y, it must go through the blocks of E. Okay. And the Y may not be a descendant on X. So both of which assures that we have the conditional independence in the network between X and Y. So if either of these, sorry, if any of these three condition holds, that is, uh, now in these three conditions, we are considering the directions to specify different conditions. But if you see the undirected case, in every case also E is blocking the X and Y pathway. So in this way, where X is the ancestor of Y, in this, where Z has two different paths in two directions towards X and Y. And in this condition, if X and Y are both coming to Z, and then Z is fanning out to different parents. So in any of these conditions, it is said E is de-separating X and Y, or E is blocking the X and Y pathway.
Ma'am, if it is undirected, then why at Z the direction is being considered?
Okay, so basically the directions are the actual, say, in our actual implementation, because when we are implementing Bayesian nets, it is um, are directed acyclic graph. So directions will be there specifying two different kind of network constructions. But we are saying that even if we overlook the direction, even for an undirected path, if we take out E, there will be no path left between X and Y. That means that not only this, there cannot be another path which goes, like, say for this, there cannot be another path which goes through some other node, say D, from X to Y. Okay. So E is the only block of nodes that is connecting X and Y. Am I clear?
Yes, ma'am.
So see an example. Say, so this is for a car. Say the battery directly influences the radio and the ignition. Ignition and gas starts the car, and this charge state moves the car. So now which two are de-separated? If I take, say, like battery and gas, these are de-separated by the ignition and the start. Okay. So these are the, say, if I take out start, or if I take out ignition and start, there will be no undirected path between battery and gas. So this is separated by the third condition. This is just an example. Is it clear?
Ma'am, can you repeat the example once?
So we said that two sets of node x and y are d-separated by another the evidence set of node e if any of these three condition holds. Now, say for example, we have a topology, a Bayesian network for a car like this. That battery is influencing radio and ignition. Ignition and gas is influencing starts, and starts moves the car. Now, if we take the pathway between say the ignition and gas or battery or gas, so if we take out the start state, say if we consider my Z to be start, so there will be no pathway if I remove Z, right? So Z is blocking, this start is blocking my pathway from ignition to gas, like if we consider the undirected path. So in this case, start is de-separating the ignition and gas. Is it clear?
Yes, ma'am. Ma'am, here also ignition and moves are also de-separated.
Yes. Yes. Yeah, the ignition and move are also de-separated. But it is only by the start. So it is de-separated by start.
Yes, ma'am.
Okay. Okay. So Bayesian nets are used in different medical diagnosis. So especially where we have the cause and effect kind of relationship. That is for medical diagnosis, for troubleshooting of hardware software system, analysis of genetic sequences, or data interpretation, or the image understanding, and computer vision. So with that, it comes to the end of Bayesian net. So does anybody has any question?
Ma'am, can you hear me?
Yes, yes, tell
Uh,
me.
like a few slides ago, uh, where you one more slide behind. Yes, here, how did you choose the ordering? Like, why did you choose the specific sequence?
So we can choose the any order. It could have been E, B, A, J, M. So
So we have to perform this thing for all the sequences, right?
no, we can choose any ordering. See, actually, uh, for probability, if you have all these probabilities, no, if you have say the A given J comma M, B give the E given the A comma B, B given A. So actually, you can also work out the other probabilities also using the Bayes theorem. So using this probability, if needed, you can actually find out P of A given B, P of the A given B comma E. It will be a bit complex, but it is doable.
But like if the order which we would have chosen would have contained A in the first place, yeah, then we would have
Yes, yes.
made
Then
an arrow directed from
but
A towards something else, but that would have been wrong, right?
no, see, because we have seen this net at first, we are thinking that this is the only desired state. But this is also one type. This is also based on one type of ordering that we choose. Okay, if we have gone the other way around, EBAMJ, we would have come up with this network. So what I am trying to say is that both of these ordering are fine. Both of these network topology are fine as long as these probability values are within the limit of the probability values. Okay. And if you have this network, you can calculate other way around, like from burglary to alarm to earthquake to alarm. Say for, yes.
Yes, I got that. But like, how do we decide the direction of the arrows?
We decide the direction of the arrows based on the ordering that we have chosen. And if needed during our actual problem statement, we will calculate the other probabilities. Or another solution, that if you have a system that can actually understand this problem statement and choose and inform the ordering based on what the end result it wants. Specifically, what we try to do when we come up with automatic mathematical equation generation from a natural language problem statement, because actually when we are doing manually, we are doing this. We have made our network in this way because at the end we need to find this, that probability of Mary not calling given the alarm has set up and also burglary happened. Okay, so that's why we are choosing this network. But this net is also fine, and this the ordering are based on like our choice. So it can be completely random ordering, or if there is any informed decision function, we can choose that ordering.
You mean so some different connections would also represent the same network?
Hmm? Sorry, can you repeat?
Like you mean that some different connections would also represent the same network?
Some different connection will not represent the exact same network. See, network is basically a graph topology, right? So if my sets of connections are different, then my graph will look different. But then these probabilities will be different too, right?
Yes. Okay, ma'am. Got it.
So it is just like how we calculate the probabilities and how we choose the network topology. So, and as I said, in this we are not going into what is the preferred way of choosing the ordering, but I am sure there will be work on that. That based on a given problem statement, what is the best possible the ordering of a Bayesian network? If we can automatically assume that. In this case, we are just assuming that we have a set of random variables and we are assigning and the order to them, and we are picking them up in that order and adding them to our network with suitable connection. Understood?
Yes, ma'am.
Yes. So we have done Bayesian nets. So can anyone please tell me that whether where is my Teams meeting? Yeah. Okay. So can anyone please tell me whether this dimensionality reduction was done in the class, like PCA and the multidimensional scaling?
No.
No, right? Okay. We will cover that. So let us take a 5 minutes break. Okay.